we present Kineverse, a symbolic articulation model framework for model-agnostic mobile manipulation. When tasked with fetching flour from a pantry, a robot needs a computational model of the pantry that it can use for perceiving it and interacting with it. Current frameworks for modeling such articulated objects use a descriptive modeling scheme which does not contain how computational models might be derived. Additionally, even though models of articulated objects are subject to change as a robot explores new environments, there are no standards for exchanging such models among the components of a running robotic system. To address these challenges, we introduce a new framework for building articulation models. In this framework, articulated objects are modeled directly as their underlying mathematical functions through symbolic mathematical expressions. We also present a method for exchanging these models in an active robotic system. We argue that this framework is extensible to new modes of articulation and enables the development of articulation-agnostic robotic skills for solving common robotics problems. In our framework, articulated objects are modeled as a tuple of two collections: a collection of named differentiable forward kinematic functions of the object's parts, and a set of constraints limiting the model's configuration space. We propose building articulation models through a series of operations which represent meaningful changes to the model, such as connecting two bodies of an object. Alongside this modeling framework, we also propose an architecture for distributing these models in an active robotic system. In our architecture, a central model server stores the current model used by the application. Users of the model, such as state estimators and manipulation components, can subscribe to a subset of the model, while components estimating the model structure subscribe and add changes to the sequence of operations. We implement our proposed framework in a ROS package named Kineverse, which we use in our experiments to evaluate the merit of our approach. We evaluate our approach by using it to model a simple, novel kinematic and applying it to common robotics problems. In addressing those problems, our solutions rely only on the forward kinematics and model differentiability afforded by our symbolic mathematical expressions. We do not differentiate between different types of articulations, making the solutions articulation agnostic. We demonstrate our approach's expanded modeling capability by modeling a simple garage door kinematic which cannot be modeled with existing approaches. Our model produces the correct motion for a static garage door. The first of our robotic tasks is to estimate the configuration space pose of a kitchen from 60 pose observations of its parts using an extended Kalman filter. We evaluate the performance of our implementation with varying numbers of degrees of freedom and increasing noise in the observations. The results of this experiment show the estimator to work. We judge the estimator to be online capable at a maximum of 4 milliseconds per EKF update while estimating the state of 23 degrees of freedom. In robotic manipulation, we pick a grasped manipulation task and an object pushing task. We introduce model-agnostic controllers for both tasks. The grasped manipulation controller generates a desired motion in the manipulated object and a matching motion in the robot to maintain the grasp. The pushing controller uses local object geometry and the derivatives of the objects and the robot end effector's poses to navigate to a suitable pushing location and generate a plausible push. We evaluate the efficacy of these articulation-agnostic solutions by performing rollouts of the controllers manipulating different objects. We view our controllers as successful in achieving their tasks, generating plausible trajectories for them. However, we observe the employed gradient descent scheme to be not well suited for non-holonomic kinematics. We evaluate our approach's applicability to real-world robotics by deploying our articulation-agnostic solutions wrapped in a simple behavior on a real robotic system and let the system manipulate a few objects with differing kinematics. We use a PR2 robot with a whole-body velocity control interface as our robotic platform and repeat our tasks at least 3 times in a row as a measure of stability. We view the overall deployment as a success. Our system is able to complete the tasks successfully multiple times in a row. The lack of a dynamics model leads to the controllers not accounting for the inertia of the robot's base, yielding somewhat slow executions. We view our evaluation as successful in demonstrating that it is possible to solve common robotics problems in an articulation-agnostic way using our proposed articulation model framework. For greater details on our proposed model, the evaluation, and the link to our implementation, we refer you to the full paper and to our project page.